All right. So indeed, I'm Pierre Varjabedian, and I'm going to present to you another type of multivariate cryptographic system, which is HFE. So it doesn't work exactly as UOV that we have seen a lot today and yesterday. So I will bring here a small introduction to HFE. Then I will talk about mineral attacks that we talked just now, and the effects on mirror attack on perturbations that we are using currently on HFE. And finally, I will give you another scheme, HFE IP minus, which is a signature scheme that we have created. So as I said, it is a multivariate scheme. It was created using the fact that when you have a finite field, it can be seen when you take an extension field, it can be seen as a vector space on the small field. So you have a natural isomorphism between the two. So it was created in 1996, and since then many variants have been created. So what is the general structure? So first of all, instead of all previous material scheme which we've seen, the private key is not a multivariate scheme. It is only an univariate polynomial. So here we have H, which is of a special form, which only contains polynomials with a sum of 2 power of the Q, where Q is a characteristic of the small field we are working on. So with that property, when we see H in the small fields, it will become a system of quadratic polynomials. But the degree in the big field it will be relatively high. Not too high, because we will need it to be small enough to be able to solve it through root finding algorithms such like Berlekamp. Obviously, we all know about the natural morphisms that I noted here, which is phi. So we need to hide this structure with 2 linear transform T and S. For a signature, in order to sign, I will just describe it slightly. I will not send you in details because the signature is a bit more difficult than what I was going to describe. But overall, you just send a vector y, and you're trying to find solutions. So x1, xn, such as that p of x is equal y. It is hard in the small field because you have to solve what looks like a random quadratic system of polynomials. But in the big field, it is easy because, as I said, you just have to find roots for a polynomial. All right. So since the creation, some attacks have been found. So we have Grosvenor basis attacks and Minranx attacks. We have created since then, or they were created before, but they were used later on to counter the attacks, several variants, so minus and vinegar, for example. Quite recently, a new type of attack was found, and that's made these variants inefficient. In the previous NIST competition, there was a scheme based on HFE, which was called GEMS, and just was broken during the competition. So in order to conduct a Minranx attack, I will need to have a matrix representation of our problem. As you can see, I have noted S and T just like earlier, and Mn will represent the phi isomorphism. It is important to note that the H have a special form, which is to only have a small block A of size d times d, and everyone else is 0. So min-rank problem. So you need to have a set of matrices, and you want to find a linear combinations of this set of matrices of small rank being R. So in order to conduct a migration attack on the matrix T, which means that we want to find the coefficients of T in order to find then the rest of the key. Well, it's quite simple. You just have to take T that's in the side. It's now a min-rank problem with a rank of R, which is the rank of the matrix H. So it's not R, it's more like small d now in our case. We can conduct another attack on this time on the matrix S, but it's a bit more difficult to explain. So we need to recall that we have this expression of our public key. And if we move this matrix SMN and on this side, we now have a min-rank problem if we take the first row of each H star O. I forgot to explain that each H star O represents the matrix H to the power of the Frobenius. So it's just like when you are doing the natural morphism between finite field and the big field. So as I said, you take the first row of each H star I, and you obtain a new matrix. Because of the structure of the Frobenius morphism, you have now a new matrix that will have this type of form. So we understand that this matrix only has a rank D again. Why is that? Because when you take the first row each time, it will do something like that. You will have the first row here. Then, because of the Frobenius, it will rotate, essentially. This coefficient is not the same as this one, but essentially it's just a rotation. So you have a lot of zeros because of the structure of the matrix H. So if we talk about the minus perturbation, it's quite simple. You take the public key and you do not reveal all of the polynomials. You will only reveal some of them. So this perturbation is quite efficient against Grubner attacks and min-rank attacks, but it has no effect on the attack on S. And we're not explaining details why. I will present to you now another variant. It was created far earlier. So in this variant, we add to the central map H another quadratic term, which will be of small rank. But this time, this quadratic term, as you may notice, even if it's of small rank, the matrix will be full. And it is quite important to notice that. So overall, the attack on T does not change a lot because of the fact that the attack on T only relies on the rank and not the form of the matrix. So the rank of the Thompson map will be D plus pi, where pi is the rank of the added perturbation. So the attack is slightly harder, but not that much. On the other hand, the attack on S is quite changed as the matrix Z is full, so H will become full also, And the Frobenius will now break all of the linear bounds that were on the matrix Z. So the rank is highly increased, and we have no form of proof of that, but we have noticed that the rank is higher than n out of 2, which is extremely sufficient to counter all attacks on S. So why is that so? As I said, we take the first row of each matrices. But now, as the matrix H is now full, all of these matrices have non-zero rows. And the rows are likely independent. So obviously the rank will be increased. So we have made here a summary of all variants that we know on HFE. A lot of them haven't been mentioned earlier. We have projection, plus hat, and so on. All of them have similar properties. Overall, it's a trade-off. They have either no effect on the min rank S, or have one, but do not have an effect on min rank T, and vice versa. IP is different than all of them because it has effects on both of them, and the effect on S is dramatically it's far more important than what we were used to. Bear in mind that all of these variants do have a cost. So if we want to use the variance minus, for instance, in decryption, it will have a high cost. On the other hand, if we use it on signature, it will be almost free. IP do have the same cost in signature and in decryption. So I will present to you a new scheme, HFE IP minus. Why is that scheme? Because as I said, -2 do have effects on Grobner attacks and min rank T attacks. On the other hand, it does not have any effect on my min rank S, but IP do have effects on min rank S. So the combination of both of them will be supposedly efficient. So we proposed a set of parameters here. So this set of parameters tries to be as fast as possible, but being secured and having a small signature in the end. We have another set of parameters that have even better signature size, but it's much more slower. So I want to note that the size of the signature are in bits, not in bytes. So it's very, very small. Nonetheless, you may also notice that this size is less than two times the parameter security parameters. So we would be vulnerable to birthday paradox attacks. But we are using something that I will not describe here, which is called the Festel-Patarin. It was introduced earlier and was used for gems, for example. So a few highlights. So our scheme is interesting because it is a very, very small signature scheme. I do not know a lot of signature schemes that are able to have this signature of this size. It is post-quantum, obviously, but it is extremely slow, and the public key is very big. Well, thank you very much, and I hope you enjoyed, and I will be pleased to answer to your questions.
Any questions? Okay, maybe just one small question from me. So, yeah, you mentioned that the public key is very big, and you know that existing UOV-like schemes like to add some structure things in the scheme to reduce the public key size. And do you see this can be done for your
Um,
signature scheme or?
Well, we haven't tried anything about it for the moment. We do have, to be fair, we do have similar key sizes as gems. I'm not quite sure. So they didn't try, obviously, to reduce public key sizes, but I'm not sure it is as efficient as in UOV. But to be fair, we haven't looked on it, so I'm not sure I can answer to your questions properly.
Okay, then.
So thank you for your talk. So it's indeed a challenging question to work on HFE. So I think the bounds that you show for a direct Gromner's basis attack are upper bound. So do you try to extrapolate a bit more precise bound? So I think they are a bit optimistic. And the parameters that you select looks very aggressive. So do you try to perform directly Gromner basis computation to figure out the degree of regularity?
So no, we haven't looked on direct attacks that much. Our parameters are aggressive indeed. Nonetheless, I'm in fact, if I recall well, the attack on T are always better than the Gromner basis attacks for what we have found. So I'm not sure that Gromner basis attacks would work on it. Yes. If we compare to gems, for instance, I think we have more minus than them, which would be detrimental to the attack. I think IP do have an effect on Grobner basis too, which is of the same kind. So it will increase in the formula. You have something like Q plus A plus V and so on. You would have also plus IP. So I don't think we are too worried on Grobner basis attacks.
Okay, and let's thank the speaker again.